All right, so 2.6 is, it talks about nonlinear inequalities. We've done linear inequalities where you have like x minus 3 is greater than 5. You take x to, you take 3 to the other side, and you get x is greater than a number, then you have the solution on a number line. That's algebra 1. Now, when we have a polynomial inequality, right? A polynomial inequality has the form f of x is less than or greater than 0. So this one, for example, it says f of x is less than 0, or, it could look like this, f of x is greater than or equal to 0, okay? What that is telling you is you want your function to be greater than or less than 0. So in pre-calc, we really, we want to make sure that when you see something like this, greater than 0 or less than 0, that in your mind, it does translate to just positive or negative. So if I see blah, 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 greater than 0, positive, blah, 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 less than 0, negative, all right? Now, based on what this inequality symbol is, what we're looking for is portions of the graph which are positive or negative. So let's just talk about what that means for a minute, right? If a graph is positive, right? So if I want to say f of x is greater than 0, if a function is positive, then it lies above the x-axis. So if you think about it, the x-axis divides the region vertically into two regions, right? The part above are all your positive values of y. The part below the x-axis are all your negative values of y. So if I say f of x is greater than 0, I want the regions where my function is positive. So that's this region here, that region there, and that's it for this, right? So all that in the red are the regions where f of x is greater than 0, where the function is positive. Now, if I say f of x is less than 0, then those are all the regions where the graph is below the x-axis, okay? So what we want then is we want to find the values of x. So we want to find values of x where the graph is above or below the x-axis. Okay? Now, we say f of x, right? But that's not the only way we can refer to a function. The function can be called h of x. That means the name of the function is h, but the variable is x. A function can be called v of t. That means the name of the function is v, like velocity, and then the variable inside is t, right? It could be, let's say, h of r. All right, the function is h, like the height of something with respect to its radius. The variable inside is radius, right? So don't let that confuse you. Whatever the notation is, you just have to focus on the positive and the negative regions when we're doing nonlinear inequalities. Okay, to solve one of these equalities, we have to solve f of x, right? Solve meaning, you factor, whatever, you solve it. You get values which make it 0. You plot the zeros on a number line, and we're going to create a sign chart. We've done a little bit of this when we did domain. And then we're going to test values from each interval. So let's just do this first one here. You know what, before I do that, let's talk about multiplicities a little bit. So look at this. Each one of these points here are zeros, right? I have a 0 here, 1, 2, 3, 4 zeros here. So do you see in the first 3 from the left, it seems like this, not it seems like, the graph has an odd multiplicity at the zeros. Do you see that?
Yeah.
At the odd multiplicities, what happens? The graph changes from negative to positive and vice versa. So here there is an odd multiplicity, and the graph went from positive to negative. Here there is an odd multiplicity, it went from negative to positive. At the points where the multiplicity is even, the graph will remain in the same region. So if it was in the negative region, it'll remain there. If it was in the positive region, it'll remain there. All right? So f of x changes sign at odd multiplicities. So for example, suppose f of x is like x plus 2 times x minus 1 squared, right? It will change sign here. So at negative 2, it'll go between negative and positive and vice versa, right? But at positive 1, it'll stay in the same region. All right? Okay, that's helpful later on. All right, so let's do this one. If we want to solve this one, first it must be set equal to 0. So we're going to say x squared minus 8x plus 15 is less than or equal to 0. Okay, now this factors as x minus 3, x minus 5, less than or equal to 0. This is where you start solving. You want to compare it to 0. You want to make it less than or equal to 0, not less than or equal to 1, right? Because that's where you test whether it's positive or negative. All right, so now from these two, we extract what values of x for zeros? 3 and 5, and those go on the number line. Okay? Okay? Now, I'm going to test. So that's what we did here, a sign chart. Now we're going to test values from each interval. We have 3 intervals here. And I'm going to test values. So what I'm going to do is I'm going to plug values into here. So plug into this. Now, you can plug values into any of the steps where it's comparing it to 0. So not the first one, but here and here. I like to plug it into the factor form because it's so much easier, and I could see multiplicities, and I could do my alternating signs and all that good stuff. So here, my favorite obviously is always 0, right? So when you plug in a 0 into the first parenthesis, it gives you a negative value. Into the second parenthesis, it gives you a negative value again. Together, that makes positive, right? So that's essentially the idea behind it. If you plug in a 4, and we're not going to do it like this every single time. If you plug in a 4, the first parenthesis gives you positive, then negative, that makes negative. And then if you plug in like a 6, you get positive, positive, which is positive. Okay? Now, what I want are the regions where this function is less than or equal to 0. That means the region where I got negative, right? Where I got minus here. All right? This is less than or equal to 0. So the solution will be from 3 to 5. Okay? Closed here, less than or equal to 0, I include the 3's because when I plug in a 3, the function is 0, I can take those. When I plug in a 5, the function is 0, I can take those, and everything in between. So I did this very, laboriously like this. We're not going to do it like this from now on. We're going to do multiplicities. So you plug in the 1 here, you get positive here. At x equals 3, you have odd multiplicity. That means it must switch sign. So now you get negative here. At 5, odd multiplicity, you get positive afterwards. Okay? 3 to 5, that's the solution.
But if it was x minus 3 squared, it would be even multiplicity and it would stay the same size?
Yeah. Okay, so this next one, it's going to be x cubed minus 3x squared minus 22x plus 24 greater than 0. Okay, so you can't do this by factoring, right? There's so what you have to do is like P over Q, like we were doing before, right? So what are the values of P over Q here? If the leading coefficient is a 1, then it's just the values of P. So it's plus or minus 1, 2, 3, 4, 6, 8, right? What else?
12.
And 24. All right. So you have to try each and every single one, blah, blah, blah. Or remember, you could use your calculator to figure out a value where it's 0. All right. You know what? Let's just do 1. Let's see if it works with 1. I know it does. 3, 2, 1, 0. Okay, so 1 comes down. Negative 2, negative 2, negative 24. Oh, look at that, it works. Okay? Right, so now what this is x minus 1 times x squared minus 2x minus 24 is greater than 0. And how cute is that? That factors. Okay, so now I have 3 points, 1, 6, and negative 4. Okay. All right, multiplicities are odd again. My favorite is 0. So if I plug in 0 into the first one, I get negative, then negative again, then positive. So that makes it what? Huh? Positive, right? Where is 0? Okay, so now each of these have odd multiplicity, so they're going to alternate, right? So the one to the left of it is going to be negative, and then negative here, and positive there. Okay, easy as pie, that one. Minimal thinking. Now, which regions do I want, positive or negative?
Positive.
I want the positive regions, so that's here, and that's there. Now, I don't want the actual values that make it 0 because it's just strictly greater than 0 here. So they're open parentheses from negative 4 to 1 and from 6 to positive infinity. All right? Huh? Okay. These next ones are my favorite. Okay. So this one here, can it factor? No, it doesn't factor. Right? So then I still need points on my number line. All right? But it doesn't factor. But if you look at it closely, if you have positive values here, right, of x, what is the whole function? Does it become positive or negative? Positive, right? If you put in positive values of x, this entire function will be positive, right? Now, what if you have a negative value of x? Let's think about that for a minute. Let's say you have negative 5, right? Negative 5 squared is 25, okay? And then what about this one? So that's positive 25, negative 10, the positive is still winning, and then you have a positive 3, so it'll be a positive number, right? What if you have hang on, Elon. What if you have a different negative number? So think about it. Whatever number you have, if you square it, that value is going to be larger than if you multiply it by 2. Is that right? So you're always going to have a larger positive than a negative. Suppose you take negative 10. Negative 10 squared is positive 100, large number. Negative 10 times 2, merely negative 20. So the positive, that square, is always going to win. Which means, are there any values for which this value is, this function is negative? No, this function is always positive. All right? Are there any values for which this is 0? There are no values for which this is 0 if you look at it, because if you do the quadratic formula on this, you get an imaginary number, right? So basically, yeah. So basically, what type of function is this? Quadratic, cubic, quartic, what? What type of function? Quadratic, which gives you a parabola, and it's always positive and it's never 0, so it sits above the x-axis like that, right? So now, what am I going to do here then? I still do my little number line because it makes me feel nice and safe. This is 0. At 0, this is positive. For larger values, it's positive. For smaller values, it's positive. This function is always positive. So then, when my question asks, where is f of x less than 0? It's never less than 0, so it's no solution. You could do no solution like that as an empty set. You could write no solution, all right? Don't write no, because I don't know what that means, okay? Now, this is telling you, okay, next one, same function. Now it's saying, where is it greater than or equal to 0? Okay, when you have greater than or equal to 0, two situations could satisfy this. Where is it greater than 0? Always. Where is it equal to 0? Never. But either or satisfies this. Where is it greater than 0? Always. It doesn't matter that it's never equal to 0. So here we're negative to positive infinity. Okay, so it either has to be greater than 0 or equal to 0, and it qualifies. Okay? Even if it's never 0. So think about it this way. Suppose I said there is, like, I don't know, we're going to have ice cream outside, and anybody who's greater than or equal to, I don't know, 14 years old can go. So who from this room is 14? Nobody. But can you all go? Yeah, you could all go. All right? So you either have to be older than 14 or equal to 14. Okay? All right. Here, okay, this is a different function, but I love this function. Okay, so now this is telling you blah, 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 less than or equal to 0. Okay, let's see if we can factor this guy. You know what? We actually can factor him. This is a perfect square trinomial. Okay, so all we get here is negative 6. Okay? All right. When x is 0, is this function positive or negative? Is it ever negative?
No.
Right, so it's positive here, and then it's got even multiplicity, so it's got to be positive there. But how about at x equals negative 6? What's the value there? 0. 0. Now this is telling us, this is asking us, where is this function? Less than or equal to 0? At negative 6. So where is it less than 0? Never. Where is it equal to? At negative 6. So the only solution here is negative 6. That's it. Squared. That's a 2. Oh, I'm sorry. All right. So at x equals negative 6. Now, here are some ways you can write this. You can say negative 6 in set notation. You could say x equals negative 6 like this. We don't do this, though. Not that. I've seen that before. Not that. Okay? So now, what if it asked us this? What if the question was this? X plus 6 squared is less than 0. What would it be? No solution. What if it was x plus 6 squared is greater than 0? Ooh. Strictly greater than 0.
It would be negative infinity to comma 6.
Right, everywhere.
6 comma infinity.
Right.
Because it's 6 is 0.
Okay. What if it was What if it was x plus 6 squared greater than or equal to 0? All real numbers, right? All right, so again, there are, so this is one, okay, this is a fantastic test or final exam question, right? Because how much calculation is there? How much tedious calculation? Little to none. Does it test your understanding? It does, right? Do you have to work the mind a little bit? You do, okay? Those are the good questions, okay? All right, now let's do, so these were polynomial inequalities where they were all polynomials. Let's do some rational inequalities. Rational fraction, right? A rational inequality is one that contains a rational function where you have a variable in the denominator as well. So the only difference is this. Whereas for the polynomial functions, we were looking at multiplicities, right, for the sign chart. In a rational function, the sign can also change at the point of the discontinuities. So the sign chart of a rational inequality must also include the zeros of its denominator. This should say denominator. Right? So basically, same exact thing. You do the same exact thing, except you also put on the sign chart the zeros of the denominator. And I'll tell you right now, for these, I want to say like 75% of the mistakes are when students, they just forget about the denominator, right? You know everything else, you just forget the denominator. Okay, so here, let's do this one. Basically, what we're going to do is figure out where the zeros are. So where are the zeros of this function? X equals negative 4 over 3. And then in addition to that, we want to figure out where the discontinuities are. And it doesn't matter. We're not discriminating. We're not going to discriminate between discontinuities, right? We're going to take all of them. Equal opportunity. X equals negative 2. Whether it's a whole, removable, non-removable, infinite, jump, whatever. So now we do our sign chart. Yes. The zeros are where the numerator equals 0. So I set that equal to 0. Yeah. Now, at x equals 0, right? What do I get? I'm going to plug it into here. What do I get on the top? Positive or negative? Positive. What do I get on the bottom? Positive. Positive divided by positive gives me positive. Now, where did I get the negative 4 over 3? Here. Multiplicity is even there. I'm sorry, it's odd there. So it alternates sign. Where did I get the negative 2? The bottom. Odd multiplicity alternates sign. Plus, minus, plus. Now, I want the value, I want the regions where this function is positive or equal to 0, which means it's this region and this region. So, negative infinity to negative 2, close that negative 2. Oh, no. Do I close it at negative 2? Because it's a discontinuity, but I do close the negative 4 over 3 because it's 0. Okay? We're good with this? So, if this was on a test, I write the solutions here, and then I say, okay, you know, they get a point for coming up with the correct points. You know, you get a point or 2 for the correct signs here. You get a point or 2 for figuring out the right regions, and then a separate point for, you know, whether it's open or closed properly. All right? It could be. Okay. So here, sorry, this is a rational equation. When you just have two terms, you can either cross multiply or it's the same as multiplying both sides by the LCD. So here we're going to have x squared minus x minus 11 less than or equal to 3 times x minus 2. Okay, so x squared minus x minus 11 less than or equal to 3x minus 6. That's how you solve rational functions. All right, so now if I move everything to the same side, I'm going to get x squared minus 4x minus 5 less than or equal to 0. When I factor this, I get x minus 5, x plus 1 less than or equal to 0. Okay, so my sign on my sign chart, I'm going to get -1. And what other number? And is that it? You also have to put in the 2. Okay, don't forget the 2. Yeah, we did it. That's the thing. That's the thing. When you solve it this way, this is also why when you solve rational functions, you have to go and test for extraneous solutions, because when you do this, when you get rid of the denominator, you're getting rid of a whole vertical asymptote. You're artificially changing the problem, right? And you have to account for that later. Okay? Yeah. So, yes.
I did it like I multiplied 3 by x minus 2 over x minus 2, and I kept it.
Same exact thing.
So you don't have to get rid of it.
Right, but then you're still solving. Yeah. But then you're still solving just the numerator. So, okay. Now here's the important part. Here is the important part. Where to plug it in? Like we said, when by the time you got here, you have changed the entire problem. So when you're going to plug the numbers back into an equation, you have to go back to the original. And what you're going to do is you're going to take this function here, x squared minus x minus 11 over x minus 2. So the thing is, you can't be comparing it to 3. You have to compare it to 0, because that's where the positive changes to negative. So you bring the 3 over less than or equal to 0. Now that blue is what you're going to plug in your values into. Okay? So, again, my favorite to plug it into is what? 0, right? So when you have 0 here in the numerator, you get -11 over -2 minus 3, right? So that's positive 11 over 2, which is what? 5.5 minus 3. So that's a positive number, right? So at 0, it's positive. Now, where do we get the -1? Odd multiplicity changes sign. Where did we get the 2? Odd multiplicity changes sign. All right, so it's positive here. To the left at -1, it's odd multiplicity. It's got to alternate sign here. You forget about everything else. Then here at 2, it's odd multiplicity. It's got to alternate sign. Forget about everything else. Then here at the 5, forget about everything else. It's odd multiplicity. It's got to alternate sign, so it's positive there. This will help you immensely when you get to calculus as well, because over there, you're not going to be doing this specifically, but you're going to be doing other things with derivatives and this and that and, you know, against sign chart. So this multiplicity issue will help you immensely over there. Okay, let's get back to the task at hand. We want negative values or equal to 0. So the regions are here and here. Okay, can it equal -1? Yeah, can it equal 2? 5? Yes. So negative infinity to -1, 2, 5.
How do you know there's 0? How do you know it's equal to 5?
Well, because it's less than or equal to 0 here. Okay? All right? Okay. So this homework will be due tomorrow. And then tomorrow we're going to start going over chapter 3. Okay?